Okay, in this last part of the course, we are going to study the Silo theorems, which is the last topic. Silo theorems are very important part of finite group theory. They are standard theorems and they are very useful in understanding finite groups. So, before we state, there are three Silo theorems. I will state them and prove them in the next few videos. Let me first recall what we have learned in the previous videos. So, our setup was the following. So, G is a finite group. So, we are going to recall first. So, remember our setup is G is a finite group, S is a set. Okay, so most of the time we will deal with finite sets, and the assumption is G acts on S, right. So, there is a map from G cross S to S. You have an element G and an element S. We map it to what we call G dot S, or sometimes we just write it as GS, and it has the usual properties. 1 dot S is S, and G1 G2 S is G1 G2 S. Okay, so these are the properties of group action. So now, and the most important thing that we have learned in the video when we talked about group actions was the counting formula. Remember, so let us say small s is an element of capital S. So, S is the set on which G acts. So, then the stabilizer of S, we have defined stabilizer of S denoted by GS, or sometimes I will denote it by stab S, and that is all group elements which fix S or stabilize S. Remember that this is a subgroup. This is a subgroup of G. So, this is a subgroup of G, and the other important set that we have attached to small s is orbit of S, which I denoted by OS. It is a subset of S given by GS, G belonging to G, right. So, this is the orbit, this is a subset of S. These are the two things that we attach to a particular element. So, these are attached to a small s, and the counting formula says the order of G is equal to order of the stabilizer times order of the orbit, meaning the number of elements. So, you take the order of the subgroup GS and multiply with the order of the orbit or the number of elements in the orbit, you get the order of the group. And remember, how do we do this? We observed that this follows, remember this follows because this follows from the bijection between, this follows from the bijection between G mod GS and OS. So, we take a coset and map it to GS. So, this was the proof of the counting formula. And another important property of group actions is equivalence classes. So, the action of G on S partitions S into disjoint orbits, right. So, if S is finite, if S is a finite set, then we can write the order of S or the size of S or the number of elements of S as the sum of sizes of disjoint orbits. So, let us call this O1 O through O2 OK, where O1, OK are distinct orbits. Remember that orbits, two different orbits are always disjoint. So, two orbits are either distinct or they are either disjoint or the same. So, you can always use this. So, these are the two important equations that we have attached to a group action. We have the counting formula which says something about the order of the group, and then we have something about the order of the set. And the most important actions for us in the context of Sylow theorems. So, we are interested in the action of a group G on itself. Remember that the two equations that I recalled for you are general statements. Whenever a finite group acts on a finite set S, they hold. But we want to focus in these videos on the group G acting on itself. So, in other words, the set is also S, set is also G, and we are interested in the two important actions are the following. So, one, G acts on G by left multiplication. Remember, this means the action is given by G dot, let me use the word letter S. So, G and S are of course in G, but I want to distinguish between the group element and element when thought of as a set. So, this is just action. So, multiplication on the left. The other important action of G on itself is by conjugation. So, here G acts on S by conjugation. So, GS is defined to be GS G inverse. We checked in our earlier videos that these are actions on of G on itself. So, this gives the important class equation. This was the other important thing that we have learned about group actions. The action of G on itself by conjugation gives us the class equation. What is the class equation? So, we can write the order of G as order of conjugacy classes. So, C1 through Ck are conjugacy classes, distinct conjugacy classes of G. Recall that conjugacy class, remember what is a conjugacy class? Conjugacy class is simply orbit, it is an orbit for G acting on itself by conjugation. Okay, so I won't go into details because we have discussed this, except to say that class equation. So, there is a class equation for every finite group. We can compute in principle class equations of any finite group. In I will recall for you, for S3 order is 6 and there are 3 conjugacy classes of orders 1, 2 and 3. So, this is the class equation of S3. Okay, so, now this is all for recalling. Let me now go to the new stuff. So, I want to in this video set up the Sylow theorems, first Sylow theorem and prove it. So, for that, in these 3 theorems that we will call Sylow theorems, we are going to repeatedly and alternately use G acting on itself by conjugation, sometimes by left multiplication sometimes. Okay, suppose G acts on itself, consider the action of G on itself by left multiplication. So, one of the first of the two operations I mentioned of a group on itself. So, this is the option action of G on on itself by left multiplication. So, now I want to define, we want to now define an action of G on subsets of S. Okay. So, we know that G acts on itself by left multiplication. Using that, I want to define an action of G on subsets of S. So, S is actually G on subsets of G. So, suppose, so let A be a subset. So, I want to stress here, it is only a subset in general, not necessarily a subgroup. So, it is just a subset, it is some collection of elements of G, and let small g be an element of the group. Define G dot A. The definition of G dot A is very natural. So, it is G A as A varies in small a varies in capital A. So, I will leave it as an exercise for you, and this is a very easy exercise. So, if you recall or define the power set of G, right. So, this is P of G is the set of all subsets of G, right. So, G the above action. So, what I defined earlier defines an action of G on the power set, right. So, I have defined G of A to be G A, G times small a as small a varies in capital A. So, now you can define this for any subset. So, I claim that it is an action of G on this new set, namely the power set. What are the conditions to check? Identity times any subset is itself, that is clear, because if G is identity, G times A is just A, and similarly the associativity property holds, which is trivial to check. So, we have an action of the group on the power set. So, now let us fix a subset of G. Let us fix a subset of G. What is the stabilizer of A? Let us explore this. What is the stabilizer of A? Okay, so remember stabilizer is, so I am going to use this notation, stabilizer of A is all group elements such that G A is A, that is all. So, stabilizer is this. So, I want to stress here that G A equal to A means, what does it mean? So, the set G A as A in A, which is exactly G A, is A. So, in other words, if A belongs to A, then G A, if A belongs to A, then G A also belongs to A. This is the meaning of small g stabilizing capital A. So, it must have the property that if small a belongs to capital A, then small g A belongs to capital A, then we say that it stabilizes capital A. In particular, it is not necessary that G A is equal to A, right, that is not necessary. G A is equal to A need not happen. So, we do not need G A to be A. So, it is not necessary. We need that G A is again in A. So, certainly G times capital A equal to capital A does not mean G times small a is equal to small a. So, with that, now suppose, suppose that So now let us go back to the general situation. G is a group acting on itself by left multiplication. Okay, so now we are in the general situation that G is a small group acting on itself by left multiplication, and I have extended that action to subsets of G. So now let us look at the following situation. Suppose that you have again G acts on itself by left multiplication and A is a subset of G. We have extended the action of G to subsets as above. Okay. Now I am going to consider, let the stabilizer be, let H be the stabilizer of A. So remember, this means it is all elements which fix the set A, not an element of, they do not fix an element of A, they are allowed to interchange elements of A. You take an element of A, small g maps it to some other element of capital A. Okay. Now I am going to prove that. So this I am going to prove a small lemma here which I will use later. So the lemma is the order of H divides the order of A. So whenever I use this vertical bars, I always mean order of that set, meaning the number of elements of that set. Okay. So and also I must tell you again that in the all the videos from now on, G is a finite group. So we assume that G is a finite group. Okay. So what is the proof of this? So I want to show that order of H divides order of A, and the reason is, remember, H is the stabilizer of A. So let small a be in capital A. Then since H stabilizes A, HA is in A for every H in H, right. So the set, in other words, the set HA as H varies in capital H is contained in capital A, right. So the I am going to call like this, I am going to write it like this: the H orbit of A is completely inside A. Is that clear? The H orbit of small a is completely inside A. What is H orbit? H orbit is simply what I wrote earlier. So H A, small h A as small h is in H. H orbit is simply the orbit of A as you take elements of capital H. I am calling it H orbit as opposed to orbit because I now have a different group, right. Earlier I am considering G action, now I am considering H action. So orbits are dependent on the group which is acting. So to stress that, here I am looking at the action of capital H, I am talking about H orbit. So the point is, capital H is the stabilizer of A. So if small a is in capital A, the H orbit of small a is completely inside A. So in other words, hence A is the union of H orbits, right, because remember H orbits are, so of course H orbits are disjoint and A must be the union of Y. Why is this? Why is it a union of H orbits? Because if A belongs to A, then the H orbit of A, let us denote by H orbit, is completely contained inside A. So what is H orbit? I am going to write it as HA because it is small h times small a as small h varies in capital H. This is simply the right coset, right, this is the right coset of A. So H orbit, if small a is in capital A, the entire right coset is in capital A. So A must be a union of HA. Of course, the HA will be same for different A's perhaps, HA may be equal to HB, but they cover A, there is no problem. Now also we know that cosets are disjoint, so we can write A as, so in fact we can write A as a disjoint union of cosets, right. So we can write H as A as some HA1 disjoint union HA2 disjoint union HAR, right. So because again remember cosets which are equivalence classes for a group action are either same or they are disjoint. So A is a union of HA because every small a is in some HA, namely it is in HA, and they cover A of course, hence they cover A. The important point is HA is all of HA is in capital A. So we have this, and once you have that, we just identify the distinct ones among them and write it like this. So A is a union of HA1, HA2, HAR. So in particular the order of A is equal to the order of HA1 plus the order of HA2 and so on up to the order of HAR. Okay. Now let us see what is the order of HA1. Order of HA1 is just order of H. Similarly, order of HA2 is order of H. Order of HAR is order of H again. So this is order of H times R. So order of A is equal to R times order of H. This means exactly that H divides order of H divides order of A, right. This is the meaning of dividing, and here we are only using the fact that, so we used, if you have HA, remember if you have take a coset of a subgroup, left or right it does not matter, the order is the same because it is a group property. Small HA, as you vary H, will be, there will be as many elements as there are elements of capital H. So this is an easy exercise that we have done in the previous videos. So this proves the proposition, right. So let us recall the proposition or lemma I called it. If you have G acting on itself by left multiplication and you take a subset of the group G and its and the subset is called A and H is the stabilizer of A, then order of H divides order of A. Okay, this is important for us when we do proofs of Silo theorems later on. So now let us go ahead and start our discussion of Silo theorem. So now our goal is to study, so we are going to prove Silo theorems. Okay, there are 3 Silo theorems. I am going to state them and prove them one by one, but they all have to do with the following setup. So let G be a finite group. Let G be a finite group. So I am going to, Silo theorems are very important theorems to understand something about finite groups. So we understand this in the following way. So let P be a prime number. So we are going to write, suppose the order of G is n. So we are going to write n as Pe times m, where P and m are co-prime. Remember that co-prime means P and m have no common factors. Because B is a prime number, it does simply means that P does not divide m. So this only means in this situation P does not divide m. Okay, we can always write any number like this. So n equals P power e times m. See, for example, if n is 6 and P is 2, we can write 6 as 2 times 3. If P is 3 and n equal to 6, we write 3 as 2, 3 times 2. But if n equal to 6, so here E equal to 1 and m equal to 3. So write 2 power 1, here also E equal to 1 but m equal to 2. Now on the other hand, if n equal to 6 and p equal to 5, how do you write this? It is 5 power 0 times 6. So E is 0, m is 6. So E is, in this description, E is always non-negative, right, and m is always at least 1. So n is at least 1. So it is a finite group, so it must have at least one element. So we have this situation. So we simply look at how many times p appears in n. It may not appear at all, like when it is 5 and n equal to 6, or if n is 12 and p is 2, we have 12 equals 2 square times 3. So E is 2 and m is 3. So we simply look at how many times a prime appears. So now Sylow theorems are really statements about special subgroups of a group G, and these subgroups are described by the element P. So the important definition for us in this is so G is a finite group as above, a Sylow P subgroup of G is a subgroup of order p power e. So we of course write, it is important to write this. So the order of the group is written as PEM. So a Sylow P subgroup of G is a subgroup of order PE, where PE is the largest power of P that divides the order of the group G. Okay. So a Sylow P subgroup is a subgroup of order p power e. So as an example, a Sylow 2 subgroup of S3 is a subgroup of order and if you recall our study of S3 in the previous videos, S3 has 3 Sylow 2 subgroups, because it has 3 elements of order 2, each of them generates a subgroup of order 2. So there are 3 Sylow 2 subgroups of S3. On the other hand, S3 has only one Sylow 3 subgroup. So I want you to get used to this notation. What is a Sylow 3 subgroup of S3? What is the order of Sylow 3 subgroup? Remember, 6 is written as 3 power 1 times 2. So a Sylow 3 subgroup has order 3, and there is only one subgroup of S3 which has order 3, and S3 has no Sylow P subgroups if P is not equal to 2 and P is not equal to 3, because if P is not equal to 2 and P is not equal to 3, that prime does not divide the order of S3, which is 6. So PE will be P power 0, so there is no subgroup of that order. So we only consider this. So this is a convention, we only look at Sylow P subgroups if P divides E, P divides order of groups. So in other words, in my notation, small e is positive. On the other hand, if G is a group of order 100, a Sylow 5 subgroup of G, let us think about it. What is, see, 5 is a prime that divides 100. So Sylow 5 subgroups can be studied. So what is the Sylow 5 subgroup of G? What will its order be? It will be order 25. This is because 100 is equal to 5 squared times 4, right, 25 times 4. So a Sylow 5 subgroup will have order 5 squared. Similarly, a Sylow 2 subgroup of G has order Now 4, because 100 is 2 squared times 25. So CeLO 2 subgroup will have order 4, 2 squared. So we look at the largest power that divides the order, not just for CeLO 2 subgroup, it is not 2, it is 4. Similarly, for CeLO 5 subgroup, it is 25. So these are CeLO P subgroups of a finite group G, and the CeLO theorems are statements about their existence, their properties, how many there are, and so on. So in the I will stop this video here. In the remaining videos, we are going to state CeLO theorems and prove them, and then look at some examples and exercises. Thank you.